Welcome back to the Deep Dive, our curious listener. Today, we're diving headfirst into one of the really big, stubborn problems in modern physics. You know the one. We're talking about that fundamental clash between our most successful theories, quantum mechanics, describing the tiny, weird world of particles, and general relativity, which, covers gravity, the whole large-scale structure of the universe. The challenge, they just don't seem to mesh, especially when you look closely at this quantum riddle called the measurement problem.
Exactly. And that's where our sources today come in. They look at a really groundbreaking approach trying to bridge that exact gap. It's called Causal Fermion Systems, or CFS for short.
Yeah.
So the mission for us in this deep dive is really to get our heads around how CFS offers this potential new framework, a framework where quantum mechanics and general relativity might actually speak the same language, fundamentally.
Yeah.
A unified picture.
Okay, let's unpack that. Starting with the measurement problem itself. In standard quantum mechanics, especially if you're thinking about the Copenhagen interpretation, the basic idea is when you measure something quantum, its wave function, which holds all the possibilities, it just sort of, poof, collapses into one specific state. It's a bit weird, like you only know what card's on top when you actually look at the deck.
Right. And that measurement, that's the tricky part. Because this collapse, it isn't something that just, falls out of the main equations like Schrodinger's equation. That equation describes smooth changes over time. Collapse is more like an extra rule, a postulate, we call it, something you have to add on top to match what we see in experiments. And that leaves this big unresolved gap, doesn't it?
Yeah.
It makes the theory feel, incomplete. Why can't the theory explain itself right there? That's the question.
So this measurement problem is like a major pothole on the road of quantum mechanics. Is there any theory out there really trying to fix it properly? Which I guess brings us straight back to Causal Fermion Systems, CFS.
Precisely.
Yeah.
This is where CFS makes its big entrance, you could say. Because in the CFS framework, that collapse the wave function, that snap into a definite state, it's not an extra rule. And neither is the Born rule, the one that gives you the probabilities of getting a certain state. Instead, they actually emerge naturally from the system's own basic equations. Specifically, it comes from the dynamics governed by something called the causal action principle. You can maybe think of that principle like the universe's own internal consistency check. It dictates how things settle into the most, causally sound arrangement. So the theory inherently explains measurement. It doesn't need that external patch.
Okay, that's a really bold claim, deriving collapse instead of just adding it. But how does this CFS approach compare to other ideas trying to explain collapse? We've heard about models like CSL, right? Continuous spontaneous localization. How do they differ?
Yeah, good question. CSL tries to explain collapse by basically adding two things to standard quantum mechanics. First, a stochastic term that's like adding a bit of background noise or randomness, constantly nudging the wave function. And second, a nonlinear term, which modifies how the wave function evolves, making it sort of influence itself. Now, CFS has some fascinating similarities, but also really crucial differences. In CFS, the stochastic, the random effects, they aren't just added noise. They're thought to arise from, unknown microscopic details of spacetime itself, like background fluctuations. And the nonlinearity doesn't come from an extra term added on, like in CSL. It comes directly from the causal action principle, the absolute core of CFS. And here's a really interesting twist. The collapse model you get from CFS turns out to be non-local in time, which means the collapse isn't just an instant thing happening now. It's influenced by the system's past, maybe even its future connections. It suggests something much deeper about how quantum events are linked, different from CSL's instant effects.
Non-local in time.
Wow, okay, that sounds pretty profound and deeply theoretical. But if CFS is a real contender, it needs to be testable, right? Where does this hit the lab bench? What can experimentalists look for?
That's exactly the crucial question. And yes, there are potential tests. CSL, for example, with its added terms, actually predicts tiny heating effects, basically a slight violation of energy conservation in very isolated systems. You might, in theory, be able to detect this as faint photons being emitted when they shouldn't be. Now, what's really interesting with CFS is that the preliminary math suggests it might actually conserve energy. So those heating tests that could potentially rule out CSL, they might not affect CFS in the same way. Finding no heating wouldn't kill CFS. It's a key experimental difference to look out for.
Interesting. So different predictions for energy conservation, that's concrete. But CFS isn't just about fixing the measurement problem, is it? You mentioned it aims higher, trying to explain space-time itself. How does it even start building the fabric of reality from its own principles? It starts, quite fundamentally, the framework shows that Minkowski space, the flat space-time of special relativity, without gravity naturally appears. It appears as a stable solution to this causal action principle, assuming there aren't any interactions happening. It's like the default background. Then, when you do add interactions, fields, particles, gravity, the framework continues to build up the physics we know.
And it actually recovers the laws we already use, like electromagnetism or how particles behave. It doesn't just give some laws, but the right ones.
That's the claim, and it's pretty remarkable if it holds fully. The framework finds that electromagnetic interactions naturally follow Maxwell's equations. Matter particles, fermions like electrons, they obey the Dirac equation. And this is the really big one. When you include gravity, you recover the Einstein-Dirac equations. That's general relativity combined with quantum mechanics for these matter particles. It all seems to emerge from that single causal action principle.
So it's like a bottom-up construction. The familiar classical physics we see at large scales emerges naturally from this deeper CFS structure.
Exactly. It suggests a path for deriving classical physics and even parts of quantum field theory from a more fundamental pre-space-time level, if you like. It's aiming for that unified picture, deriving everything instead of patching different theories together.
Okay, this sounds incredibly ambitious, almost audacious, building everything from this causal action. How are different groups of physicists reacting to this? I imagine it's not universally accepted overnight. And what are the big hurdles CFS still faces?
The reactions are definitely mixed, as you'd expect. People working in general relativity, for instance, often start with Einstein's equations as their foundation. So they might see CFS as, well, interesting, maybe mathematically elegant, but perhaps not directly relevant to their day-to-day calculations, kind of outside their main focus. But researchers in quantum gravity, they're actively looking for ways to unify gravity and quantum mechanics and understand spacetime's quantum nature. They tend to be much more open to exploring foundational frameworks like CFS. As for hurdles, well, the mathematics is seriously complex, no getting around that. And showing precisely how all the particles and forces of the standard model emerge cleanly from CFS is still, a work in progress. There's a lot still to flesh out and rigorously prove.
Right. Complexity and fully recovering the standard model are big asks. So given those challenges, what's the perspective of the main physicist behind CFS, Felix Finster? Does he see it as just a theoretical possibility or something more concrete?
Oh, he definitely sees it as much more than just a mathematical game. He presents CFS as a serious candidate for new physics, a real contender. The view is that it's a mathematically solid path to go beyond both standard quantum mechanics and classical general relativity, to finally unify them into a single, coherent description of reality. It raises that huge question, doesn't it? Could this be the direction for the next major leap in physics, even with the hard work still ahead?
What a fascinating tour. We started with this deep crack in physics, the measurement problem, and ended up exploring a framework, CFS, that proposes to fix it in a really elegant way, deriving collapse, deriving space-time laws, all from one principle.
Exactly. We saw how it tackles that quantum puzzle, but also aims to build space-time and classical physics from the ground up. And it might even give us unique experimental signals to look for, like potentially conserving energy where other models might not. It really speaks to that persistent, driving quest in physics to find a truly unified understanding of everything.
Absolutely. And for you, our listener, here's something to chew on. If the fundamental rules of our universe governing everything from quantum jumps to cosmic expansion actually emerge from something as seemingly abstract as a causal action principle, well, what other deep structures, what other layers of reality might be hiding just beneath the surface of what we think we know right now? What else might emerge?